All right, so yesterday, last class, we introduced, excuse me, man, I hate them. I'm sure that's what you guys want to hear Friday morning. We talked about what's called the change of variables theorem, or what we call U substitution. So let's be very clear what we did. We discussed a technique for computing certain types of integrals. And the official name for this is what's called change of variable, but nearly every textbook or thing you're going to find online calls it the substitution rule or substitution or U substitution. But I kind of don't like calling it U substitution because there's nothing special about the letter U. You can use any letter you want. So homework number 13 gives you a chance to practice. So let's do some of these. If you look at the way the homework's set up, it has 3 questions, but there's a bunch of parts to the first 2. The first set says use the given substitution. So I'm sort of giving you training wheels. I'm helping you out. I'm saying here, here's a substitution you should try. But in general, there's nothing that's going to tell you, hey, use this substitution. So what you really need to get good at are the ones like in number 2. So let's do some examples. And you can use these examples to help you with the problems on homework 13. Excuse me. This light is like, I feel like I'm in a heat lamp, in a tanning salon or something. Please, as always, if you have any questions, I know you guys are very shy on this Zoom stuff, but please feel free to stop me at any time. So let's start with one that's very basic. So I want to compute this integral. So the observation you need to make is that you have a composition. You have 3 minus 5x is being composed with the power of 5 function. And substitution or change of variable gives us a workaround. It gives us a way to take this creature and write it as a more real, an integral that we already know. So what I'm going to do is, and I'm not going to use y like we did yesterday. I'm going to use different letters because you need to get in the habit of the variables are just they're just variables. They're letters. We're replacing one symbol with a new symbol. So I'm going to let y equal 3 minus 5x. And that means dy dx is negative 5. But what we can do is we can use this notation with this idea of what is a differential. And in that sort of notation, we can treat this dy dx as we can pretend it's a fraction. And we can write dx as negative 1/5 dy. And then the original integral is then reduced to y to the 8th dy, and then there's this negative 1/5, which we know we can write out front. So what I'd like you to do is think about what you see on the very last line. We started with an integral that was not obvious. And what we've done is we've changed our variables. So if you dig deeper into what's really happening, what you're really doing is you're going from one coordinate system to another coordinate system. And it turns out that the integral that we started with is the same thing as the integral that we transformed to. And how do we know that? Well, we verified that yesterday. We derived it using the chain rule. Okay, so again, the bigger picture, and this is one of the themes you're going to want to think about moving forward, is how do we take an unknown integral and write it in terms of an integral we can readily or easily figure out. Okay, so how do we integrate this? Well, this is y raised to the 9th power divided by 9. We have our arbitrary constant, and so we can finalize this by writing it as negative 1/45. And the last thing we must do is replace our original variable. Okay, so there's a couple important things you need to think about when you're doing these sort of calculations. First off, whatever variable you start with is the variable you must end with. So you can kind of think of this as like a currency. We started in X, we changed to a new currency Y, and then we do what we need to do. We buy what we want to buy, or we do the computation we want to compute, and then we revert back to where we started. Does anybody have a question? Okay. Okay, so let's do another one. So suppose we want to integrate this creature. As I suggested yesterday, when you're integrating and the integral is not obvious, right now that you don't have many options, really the only tool that you have at your disposal is this idea of changing variables or substituting. And what you'll do when you try to practice this is you'll learn some themes. And one of the themes I mentioned yesterday is this idea of look for grouping symbols. And so in this particular problem, I noticed that the grouping is a fraction. So my first guess to use for my substitution will be W is 6 minus 8x, which implies dW dx is negative 8. And then once again, I want to solve this for dx. And when I do that, I get this relationship. And so the original, or the original integral, is transformed into this integral, which we know to be the natural log and then the last thing we got to do is replace our original variable. So if you have a question or a comment, please let me know. We did a couple examples yesterday, and 2 of them had a fraction in them, and we handled each one of those in a different way. So not every problem with a fraction is going to be handled in this manner. So you have to look out for that. So I'd highly encourage you to check out sort of those examples from yesterday's class. Okay. Let's do one more before sort of changing tunes. So let's suppose we wanted to integrate x squared e to the negative x cubed dx. So if I think about this for a while, I might try a few things. I don't know. But after some trial and error, what you might notice is that the optimal substitution is let u equal negative x cubed. And then du dx is negative 3x squared. And then dx is 1 over negative 3x squared du, excuse me. Now, when we make our substitution, it might look bad at first, but it turns out that it's not going to be so bad. We get x squared e to the u, and then you have this. Excuse me. Now, if you think about what I said on Thursday, this might look bad. But remember, those x's technically aren't going to be there because they cancel out. Cancel out. And so if we pull out the constant, which we know is legal, the integral we're left with is just this. And then the beautiful thing about the exponential function is its derivative is itself, which means its antiderivative is itself. And so we can easily compute this. So I'll let you think if you have a question or something. I'll be back in 1 second.
So this is just like what we did yesterday, right?
This is 100% what we did yesterday, yes. These are the same types of examples. So right now we're working on homework 13, which I don't know if you saw that I posted, which is a bunch of integrals. And you're going to say, there's a lot. This is a long assignment. Well, yeah, but that's the only way you get good at it is to do a bunch of them. You know, I say the same crap over and over again, but it's so true. I mean, how do you get good at soccer? You run around and kick a ball. You play soccer. How do you get good at basketball? You take a ball and run around and dribble it and you shoot it. And then you do all kinds of other stuff like lift weights and exercise. I mean, how do you get good at baseball? You do it. The only way you get any good at math or physics or computer science or really anything for that matter is you do it. You just do it. All right, so there's 3 examples. These are exactly the same types of examples, the same sort of procedure we discussed yesterday, this change of variables. Okay, so then sort of the next question, what's that?
In the homework number 1, you've already given us what to substitute, right?
Yeah, I'm giving you training wheels. That's right. I'm helping you out. So in problem 1, I'm giving you the substitution. But in general, I'm not going to do that. Like on the final and going forward in your life, when you do integration, no one's going to tell you how to do it. I mean, it's each one of them is sort of their own entity, and you have to figure your way through it. But when we're just learning this, that's why I'm giving you some advice for problem 1. Okay, so one question you might have had is, well, what about definite integrals? So we didn't really discuss that yet, but the fundamental theorem of calculus tells us how to do it. So the fundamental theorem of calculus tells us how to compute definite integrals by substitution. So remember, a definite integral is one that has bounds. Now remember, what I'm going to write is going to look scary, but don't overthink it. If I have the composition of 2 functions f and g, and my integral looks like this, then I can easily use substitution to get a simpler integral when u is equal to g of x. So this is the fancy statement, you know, and of course these integrals have to make sense. F has to be continuous, it has to be defined on the range of G and all that. But we don't care about any of these technicalities right now. There's a time and place for that, and learning it is not the place for technicalities. So let's do an example of what I mean by that. So by the way, you should challenge yourself to see why what I wrote on the previous page is in fact correct. All right, so let's integrate from 0 to 1 of x times 5x squared plus 4 dx. So again, I get this integral and I say, how do I integrate it? I say, self, what am I supposed to do? Now, the square root has the stuff inside of it, and that is a grouping symbol. And that is a suggestion to my brain that substitution might work. So what I do is I set y equal to what's inside. And that implies that dy dx is 10x. And we can rewrite this if we'd like to say that x dx, notice I'm going to do this a little differently this time, is 1/10 dy. So you might take a moment to think about why I wrote it that way.
Is it just simple algebra we're doing?
I mean, no, it's not simple algebra, but okay, so you can think of it as simple algebra, but it's actually a little deeper. It's this idea of differentials we talked about a few classes ago. So if you can see where my pen is hovering, this is not a fraction. Dy dx is not a fraction. It is the notation for a derivative. However, we can use this language of differentials. That means we give meaning to dy and we give meaning to dx. And if we give meaning to those things, then we can pretend it's a fraction. So in some ways, what I'm doing right here is I am just doing algebra. But it's deeper than that, even though your brain can pretend that it's just algebra. So what would you guys call this in school? You would probably call it cross multiplying. That's usually what one of the silly things these teachers say for you to learn it. But that's probably one good way to think about it. Now, why would I write it as x dx? Because if you look at my original integral, I have an x and a dx in there. I have an x and I have a dx. So what this means then is that the original integral I have, which I'm going to write it, I'm just going to rewrite it to be even more clear. I get a new integral now. And what is my new integral? It is the square root of y dy with a 1/10 out front. Now, there is one subtlety. My original integral was in the variable x, but I moved on from x land. I am now in y land. And so my bounds that I started with, the 0 and the 1, those no longer apply because those bounds were where x started and where x ended. But now I need to know, where does y start and where does y end? Okay, so how do we do that? Well, the theorem that we wrote down last class in the fundamental theorem of calculus give us that. How do we find our new bounds? Notice our new bounds are what happens when we plug our old bounds into our new function. So we have to take 0 and plug it in for x, and then we have to take 1 and plug it in for x. So I'm going to change colors so that it's very clear what I'm doing. So up here, let's say to ourselves, let's say self, all right, if x equals 0, what is y? If x equals 0, y equals 4. And then if x equals 1, what is y? Y equals 9. Which means my new bounds for y are 4 to 9.
So how did you replace 0 and 1?
How or why?
Yeah, like what equation did you
I'm
use?
using this right here.
Okay.
That's the relationship between my new variable. My new variable is dependent on y, excuse me, dependent on x. Does anybody else have a question about this? Let's check the chat line. Nope, no chatting. Okay. So now we have an integral that we do know how to compute. So what are we going to compute? Well, this is 1/10. I like to rewrite this. Integral from 4 to 9 of y to the 1/2 dy. So let's go to the next page. We'll write that guy down again. 1/10 integral 4 to 9 of y to the 1/2 dy. So when you integrate this, this becomes y to the 3/2 divided by 3/2. But dividing by 3/2 is the same as multiplying by 2/3. And we will evaluate this from 4 to 9. So if you do some arithmetic, this becomes 1/5 times 1/3. So this is 1/15 times 9 to the 3/2 minus 1/15 times 4 to the 3/2. So this becomes 1/15 times 27, and then minus 1/15 times 8, which is 21/15, which is, divide everything by 3, 7/5. Notice our answer in this example is a number, as it should be because we had bounds. So I'll give you a second to think if you
So
have
we
any
can
questions.
even
What's that?
we can even factor out 1 over 15, right?
Oh, yeah, you
And
could have
then
done that. Right, absolutely. And the more this you do, you'll start doing that more often. I think what you're
okay.
saying is like here, yeah, I could have written this as 115 times the quantity. That's
Yeah.
absolutely correct, yeah. And that's normally what I would do, but when I'm teaching this, I don't want, I want you guys to be careful, because one of the most common errors that will happen for many of you is you might get to this top line, but then once you have to plug in and evaluate, the arithmetic kills you, because you
Yeah.
end up forgetting to like distribute negative signs. And so I just want to be, sort of extra careful here. So that's all. Does that make sense?
Yeah, it does.
Any other questions about this? Does anybody say we made an error? At all? Nobody? Well, you guys would all flunk. I should call everybody's 5th grade math teacher and say, what? Guys, what is 27 minus 8?
Oh wait, I didn't finish the question.
Now we're paying attention. Now the chat line's blown up. Look at this. Oh my God, Noah, thank you for being able to subtract. 27 minus 8 is not 21. It is
19.
It's 19. Very good.
Yeah, I didn't even notice
Oh
that.
my God, I can't believe we almost had to flunk everybody the week before the final for not being able to subtract. Very good. So this becomes 19/15. All right, good. Very good. See, I have to actually make errors to see who the hell's paying attention, if anybody. This is good. This is good. All right, very good. Does anybody have a question about this? All right, cool. So there we have it. Let's do, yes, what's up?
Can we do the sine and cosine one?
Yeah, which
Where
one?
both of
You have a
them mix?
particular one you want to do? Oh, like okay. Yeah, let's do
I
one.
mean, you
What's
can
that?
do question 2, part C.
2C?
Yeah, because
All
it's
right.
similar to the sine and cosine.
Yeah, okay, yeah. So let's do 2C. Let's make it even more interesting. Let's put some bounds on it. How about, let's integrate from 0 to pi over 4 of tangent to the 4th of x times the secant squared of x dx. So the thing to recognize here is that you have two functions, and they're not just two arbitrary functions, they have a relationship. One of the things that I hope you notice by doing all these examples is what's happening in all these problems is that you have an integral in the integrand. The thing you wish to integrate is a function and a constant multiple of its derivative. That's why this works. There is a big sort of elephant in the room with all these things. Every one of these integrals has a certain structure. It is a function times a constant multiple of its derivative. That's what we're seeing. So inside, I have a tangent and I have a secant, but the way to really think of this is you have a tangent and a secant squared. And the reason you need to think of it that way is because the derivative of tangent is secant squared. And so that fact alone tells me that I need to set, let's use, I don't know, let's use U. And now let's use a different letter. How about, we'll use Y. I'm going to set Y equals to the tangent of X. Why am I doing that? Because if I do that, I get that dy dx is secant squared of x. And so that tells me, for example, that dy is equal to secant squared x dx. And so what's nice if you think about the original integral, and this is something you should try to ponder, that's exactly what you see right here. This is just dy. And so what we do then is we say, okay, great. Our original integral simplifies to nothing more than y to the fourth dy. The only thing we have to be careful with are what are our new bounds.
Wait, last time you did x dx equals to dy secant squared, right?
But it doesn't matter. Yes, it doesn't.
Okay.
It doesn't matter how you write it.
No.
I mean, it's like you can write 4 plus 5 is equal to 9, or you can write 5 plus 4 is equal to 9. It doesn't matter if I write dx on the left or dx on the right. What matters is the relationship between dy and dx. That's what really matters. Okay, sweet. So what are our bounds now? Well, this is usually the hard part for most people, and it's even more difficult now because you guys retained your trigonometry just as well as like my child retains orders. You don't. So if x is, what happens if I want to do, let's let everybody know we're trying to do our bounds. So x equals 0 implies y equals 0, and x equals pi over 4 implies y equals the tangent of pi over 4. But what's the tangent of pi over 4? It's 1. So our bounds now become 0 to 1. I still remember my trig teacher in 10th grade, Mr. Witt. I wonder if that man is still alive. I could offer most of you $1,000 right now to tell me the values of tangent without looking it up, and you would all still be without $1,000. Then again, so the tangent of pi over 4, what is the tangent of pi over 4? It's 1. Does anybody have a question about this before we finish the problem?
No.
This is a fun problem. It looks scary, but it's really not. Okay, so now we went from a real ugly integral to really a baby integral. This is the kind you pray for on the test. Because what is this? This is just 1/5 y to the 5th evaluated from 0 to 1, which is 1/5 times 1 minus 0, which simplifies to, let's write it out. So this is 1 to the 5th minus 0 to the 5th, which of course is just 1/5. And that's it. Does anybody have a question? Going once, going twice. This was fun. I am so happy that How many of you joined me? 7 of you today. This is so cute. We have Leonard and Joe and Joel and Michelle and Shobit and Fink. Oh my God.
So you just skip the part where you replace the y with the secant square, right? Like the dy and that, or
What do you mean? I didn't skip anything. What are you talking about? I skipped a step.
no, like you didn't replace anything the way it should be, like back to it. That's why
Well,
I'm
I don't
asking.
need. You saying go back to X?
Go back to y, like y fourth, right? And then when you get to 1 or 5, y power 5, right? We normally press the substitute.
No. That's only in the indefinite integral. You mean substitute back the tangent?
Yeah.
No. I'm in Y land now. Now look, you're not completely wrong because you could do it that way, provided you don't change your bounds. But that's a different way of doing it.
Okay.
Yeah. Again, you're comparing apples to oranges here, but what you're talking about is how I solve the indefinite integral. These are not indefinite. These are definite integrals. These guys have bounds, 0 to pi over 4. Since this guy has a bound, I expect a number. If you would substitute back in for x, you would likely get the wrong answer because you switched your bounds to the y bounds. So you have to be very careful about this. So some of you may have learned this before, had another, maybe you guys had some calculus in high school. There's other ways of teaching this. And if you get these two ways mixed up, you could possibly get the incorrect answer. So I would advise you to pick a method that you feel comfortable with and go from there. That's just my advice. What I did there is correct. What you are suggesting could be correct, but you'd have to write it up correctly. You could also do it incorrectly. So, the strategy that you're suggesting is never changing your bounds and then switching back to X and then plugging the original bounds in. That's not wrong. So let me write out what you're suggesting and show you that it is, in fact, correct as well. So and this is a good way to finish. So alternatively, you could reason as follows. You could say, okay, our original integral is this. Now, if you want to write this correctly, you got to say this. If you do what we just did, that it does turn y to the 4th dy, but you can't put 0 and pi over 4 here unless you're very specific. So note, one way you can reason this is you can make sure the reader knows that this is x equals 0, x equals pi over 4. And then if you would like to continue in this manner, now you integrate and you get 1/5 y to the 5th as we suggested. And once again, you have to be clear that the reader knows these bounds are in terms of x. And so if you want, then you can sub back in like we had done before. So this would be tangent to the 5th of x. And now you don't have to remind us because the variables in the bounds match up. And so if you did it this way, you would get 1/5 tangent to the 5th of pi over 4 minus 1/5 tangent to the 5th of 0. But this just simplifies to 1/5. And by the way, for those of you who are still kind of confused where I'm getting these things, you have to understand the following. Tangent of pi over 4 is 1. Tangent of 0 is 0. Those are facts that you should know. Draw a right triangle if you're not convinced. And even if you draw a right triangle and you're not convinced, that means you need to bone up on your basic trigonometry. Okay. That was fun. Does anybody have a question about this? Does that make sense, Shobit? Do you understand what I'm saying there?
Yeah, it does.
Yeah, okay. So you can pick whatever way you want to do it. These are two perfectly acceptable ways. My preference, because it's more useful later on, is to change your bounds to the new variable. That is what I would encourage you to do. So I recommend you do this way. That's just my recommendation. I'm not saying you have to. I'm not going to be mad at you if you do it this way. Does that make sense?
Yeah, it does.
All
So
right.
in this one, it does. Like you just replace the use just y, right?
Correct.
Okay.
Okay.
So this same applies to the cosine one, right?
Yeah, it's the same exact thing. Absolutely. So if you look at the cosine one, the cosine has the power, so that's the composition. So to let u be your cosine. So for h, the substitution is y equals cosine or u equals cosine, whatever letter you want to do. Let me give you a couple hints before we go, because there's a couple tricky ones that might take some time for you to think. So just to get you, and by the way, my advice is to not use these hints until you need them, but some hints for the tricky ones. So for example, h, set y equal to cosine. I is a tricky one. Let's use different letters. Let's say u this time. I like to switch my letters up. I'm an equal opportunity letter user here. Let u equal e to the x. And note, and this is a part that sometimes students forget, e to the 2x is the same thing as e to the x quantity squared. So that could be useful for I. Let's see. We cover all the other ones. We've sort of covered types like that. Oh, here's one that you might not get, obviously. So for L, what you need to note is that tangent is equal to the sine over cosine. And then set y equal to cosine. N is the last one I'll give you a hint on. N is tricky. So what I would tell you to do is set y equal to the square root of s minus 1 and get creative. Whatever that means. Get creative. And then if you look at the last problem for 3, all we're asking you to do is just think of the application. Remember, these integrals with bounds can be interpreted as area. So just to help illustrate that, if I go to the next page, let's just note for 3, all you're doing is integrating. So for A, we're asking you to integrate from -1 to 2 of x squared dx. And for B, you have to integrate from -pi to pi of the sine of x. And then for C, you're integrating from 0 to 1 of x over 4 plus 5x squared dx. And then these numbers that you'll get represent the area of the region that I'm describing. So you should draw pictures. For example, if you look at part B, if I draw an XY axis, what does the sign look like from negative pi to pi? Well, it's 0, pi goes up to 1 at pi over 2 and then comes down, and then it's like this. So what answer should you expect? Well, this is what I'm trying to get you to think about. And then for this guy, what area does this represent? Well, this is a parabola. And we're interested in what happens from negative 1 to 2. So let's change colors, make it look a little. So you want to know what is the area of this region. That's what these numbers represent. So hopefully you can draw these pictures by hand or Desmos, get some feel for what's happening. Because not only do you want to be able to integrate, but you want to be able to interpret what the heck the integral's for. What does it give you? All right, does anybody have a question, comment, concerns? All right, listen, I'm going to end then. I will post this stuff to the interwebs for you to check out. Please check it out.
So
yeah, what's up?
for number 3, we should compute, right? The bounds.
Absolutely. What do you mean compute the bounds? I gave you the bounds. What are you talking about?
Like use the bounds later on to solve, right? To get a number.
Yeah, absolutely. You need to compute all 3 of these integrals to get a number.
Yeah. And then I just wanted to confirm about practice set 12, where you have to replace the x to y, or the letter you're given there. So do we have to compute there, or just leave it the way you left it?
On 12?
Yeah.
Which number are you talking? Yeah, no, you leave it the way I left it.
Okay.
Yeah, absolutely. All right.
Yep.
All right, gang. Well, listen, have a good weekend. Be safe, and I'll talk to you guys on Tuesday. Take care.